Okay, Assalamualaikum dan salam sejahtera. So today we will see a few questions regarding to boundary layer. So it may be turbulent, it may be laminar. It's not focused for test 1. So it is focused for our syllabus. Okay, let's say this question is actually taken from the textbook, but I simplified them, I mixed them. Okay, because sometimes question in textbooks will repeat so many times. So I just choose the difficult one. Okay, or the tricky one. Okay, let's say this in this question, a laminar boundary layer exists on a flat plate with atmospheric air at 20 degrees Celsius moving at 5 meters per second. At x equal 2 meters, find the wall shear, so mean the shear stress there, the boundary layer thickness, the maximum y component velocity. Okay, please read very carefully here the maximum y component velocity. Okay, the flow rate through the boundary layer. And then if we define the boundary layer thickness, we define delta to be that y location where u equal to capital U. Estimate the thickness of the boundary layer. Then find the y location where u equal to 0.5 u for the boundary layer. Then determine the maximum y component velocity at that location. So mean at u equals 0.5 u. And what is the shear stress there? Okay. So in this situation, first, the question gives you the idea of a laminar boundary layer. Okay, we have velocity 5 meters per second, and then we have location x equal to 2 meters. So at least you could imagine that we have a flat plate with the length of 2 meters here. So that is the very simple imagination of this question. So and then because it doesn't give us any velocity profile, so means that we need to solve this problem by using the Blasius solution, because Blasius solution is the representative for laminar boundary layer. Okay, so we go for the first question here. Okay, because the velocity profile is not given in this question, we may use Blasius exact solution. Okay, take properties of air at 20 degrees Celsius as follows. So we have rho 1.204 kilogram per meter cube, mu, which is the dynamic viscosity, nu is the kinematic viscosity, and this is the Reynolds number. If you calculate the Reynolds number, you will find that it is 6.65 times 10 to the power of 5. But yes, normally we assume that 5 times 10 to the power of 5 is critical Reynolds number, which is the transition between laminar and turbulent. But in this situation, maybe the surface is very smooth, so the transition is a little bit late. So means maybe with a 6.65 times 10 to the power of 5 is still laminar. So based on the question, we assume that with this Reynolds number, the condition of boundary layer is still laminar. So and then we calculate the square root for Reynolds number based on this number is equal to 815.59. So we could use this again and again in our calculation. So this is the properties that we could prepare before we start our calculation. Okay, let's say the wall shear or the shear stress at y equal to 0. So please refer to my notes, to notes of Blasius. Okay, we could calculate the from the Blasius exact solution. You may see your notes, or you could watch videos about this. So we could say that the Blasius exact solution, we could calculate the shear stress as follows. So tau is equal to 0.3321 rho u square over square root Reynolds number. So we substitute the value of rho, substitute value of u, and also the square root Reynolds number here. So we could calculate the shear stress is 0.012256 Pascal. So, and then we need to calculate the boundary layer thickness because we don't have any velocity profile. So we could use equation from Blasius exact solution. So delta is equal to 5x over Reynolds number. So, and then if we substitute the value, so the x here is equal to 2 meter according to the question, and then the Reynolds number is given in the previous page here. So we substitute in the equation, so we could get it is equal to 0.012261 meter. So please make sure that you write the unit for your answer. Okay, next, we are going to calculate the maximum y component velocity. So here, the word maximum, the y component velocity, you must know that if one molecule here, so for example, we have a flat plate here, this is the boundary layer. So what you learn in ideal flow in chapter 1 and chapter 2, if some movement from here to here, for example, okay, for sure it has component of x and it has component of y. So in this question, they ask to calculate about the y component velocity. So normally we will calculate using u. Okay, small u here in velocity profile like this will represent the velocity parallel to the air flow. So the velocity that parallel on the flat plate. Okay. So this is maybe not in our syllabus, but I found it in our textbook. So I think it is advantage for us to know about this. Okay, so according to textbooks, I think I simplified it here. You could read from textbook. It is actually start from at the end of this question, I will give you notes about this. So it is actually depends on the streamline. Okay, we know that our streamline here. So if we have one things like this, so this is our streamline, which is psi. So we have u here and we have v. So u here is actually d psi over dy. So and then v here is actually equal to negative d psi over dx. So this is Cauchy-Riemann equation, the most important equation to start your calculation on ideal flow. So this is also a part of test 1 syllabus. So please make sure that you remember Cauchy-Riemann equation. That's the very basic equation you should know. So here we are aiming to calculate the value of v. Okay, so you may refer to the textbooks. So it can be simplified that the velocity on y direction can be written as this one. So square root nu here is the kinematic viscosity times u over x times 1 over 2 eta f prime minus f. Okay, and then in this situation, okay, please remember when we solve Blasius exact solution, we do not solve by using direct integration using equation and so on, because as I said, Blasius exact solution is actually construct from the experimental work. So actually then they will have some curve fitting and so on and so forth. So in this case, okay, we will refer to tables. Okay, at this question in this stage, okay, I will show you one table that you could get from textbooks. Okay, so it is table 8.5. So in this table, they give you the value or the value of this one, 1 over 2 eta f prime minus f. Okay, and at the second half of this solution, I will show you how to calculate this value later on. Okay. So according to here, we found that at eta equal to 5, okay, please remember we take eta equal to 5 to determine the delta. Okay, so means at eta equal to 5, we found that 1 over 2 eta f prime minus f is equal to 0.8372. 9. So, and then we replace this term with this number. So, and then we could calculate the value of y component velocity. So we get it is equal to 0.005148 meter per second. So the velocity is small. Okay, that's why normally in von Karman calculation, so we just assume that all the velocity is actually moved in x direction, not in y direction. So, and then we need to calculate the flow rate. Okay, flow rate through the boundary layer. So normally we calculate the flow rate by using Q is equal to A and V. So this is the basic equation to calculate the flow rate. So it seems, so we use this equation. So normally if we have a boundary, a velocity profile like this, okay, so we take the small part here. So the small part here, let's say the velocity is moving with a u velocity, and the thickness of this small part can be write as dy. So, and then, okay, so if we just use dy and u, okay, it is not a flow rate, because normally flow rate will have a unit of meter cube per second. So meter cube here is reflect the volume. Okay, so how to get a volume in this situation? So we need to multiply with the width. So that's why we could calculate the flow rate here can be calculated by using integration of 0 to delta u times w, which is width, and dy, which is the thickness of this area. So w here is width. Okay. However, as I said, in Blasius solution, we do not derive from equation. So what Blasius did is he tried to get data from his table. So from his table, it can be simplified. The equation for flow rate can be written as this one. So width times u, nu x over u, and then f function f5 to function f0. So why we take f5? Because from the f5 here, this is the maximum or the limit for boundary layer. Okay, so means that we need to calculate all the value here. Okay, so and then we know when we integrate, so f5 minus f0, so f5 here is 0.09. So, and then F0, I'm sorry, this is F double prime. So F here is just F, so we take this one. So F5 is 3.2834. Okay, so and then F0 is 0. So we have F0 is 0 here. So we substitute here. So we put 3.2834 here. So we could calculate all of these terms. So we substitute the value. So, okay, in this situation, from the question, it not give any value about width. So, if this situation, you may assume that the width is equal to 1 meter. Okay, so this is a very simple. Or in some textbook, they will use the idea of per unit width. So means that all our question need to divide by width. Okay, so ini bermaksud kita kita anggap lebarnya adalah 1 meter kerana nilai lebar tidak diberitahu di dalam soalan. Okay, so if we substitute this value everything in here, so we could get that the flow rate here is equal to 0.0403 meter cube per second. Okay, so if when we define the boundary layer thickness, we define delta to be that y location where u equal capital U. estimate the thickness of the boundary layer. So what is the meaning of this question? Okay, as we know that in Blasius calculation, we assume that U is equal 0.99 capital U, means the thickness or the boundary is until 99% of free stream velocity. Okay, so and then if we estimate or we use idea of von Karman, okay, in von Karman, we will say that U is equal to capital U. Okay, when we use this one, so normally we could say in a boundary condition, we could say that y equal to 0, so u equal to 0, and then at another point, you will say that y equal to delta and u equal to capital U. So means that for von Karman, so he assumed that in a boundary condition, so we take a boundary limit of boundary layer at U equal to 100% capital U. But in Blasius, it takes 0.99 or 99%. Okay, so in this question means, okay, if we assume that the boundary layer is actually from 0 to U equal capital U, so what is our answer? Okay, compare with the previous one, compare between von Karman and Blasius. Okay, so again, because we don't have any velocity profile here, but we need to do what we need to take is we need to refer to table. So what table we have? So this is the table from the Blasius calculation. So because we aim U over U, because we aim U, small u is equal to capital U, so means that U over capital U is equal to 1. So we see from this column, so we aim for the 1. So we could get here. Okay, and then from this table, we could say that if we take U is equal to capital U, so we need to take the value of eta equal to 7.5. So now our calculation need to base on value for 7.5. Okay, so we take eta is equal 7.5. So and then we could calculate by substitute the value of eta here, 7.5. We could substitute the value of u, substitute of nu, and x, y, and everything. So we could get the value of delta is equal 7.5x Reynolds number. So, and then we know that the value of x here is 2 meter. So we could calculate the delta is 0.01839. So if we compare this answer with the previous one that we get here, okay, so the percentage, the difference is around 33%. Okay, tadi siapa tanya?
Saya doktor. Untuk value eta equal to 8 tu pun U over U dia 1.
Okay. So memanglah kita ambil 8 pun 1 juga, tapi 7.5 pun 1. Tapi kita kena ambil 7.5 kerana apa? Kerana ini, kalau awak table ni awak tengok yang lebih panjang, nanti dekat sini semua akan jadi 1 ni. Okay. Jadi kalau dah semua sekali sini 1, so kita akan ambil nilai yang pertama kali lah, dia menjadi 1. Kerana kita ingin mencari borderline kalau kita buat boundary layer tu. Okay. Okay, dekat sini kita anggap okay, U di sini sama dengan capital U. Nanti bahagian yang atas ni semua, bentuk dia dah memang sentiasa sama dengan capital U. Bawah ni dia start lengkung macam ni. Jadi tak logik lah kita nak ambil nilai pada nilai yang di atas lagi. Boleh imagine?
Boleh.
Okay. That is the situation. Okay, so so di sini kita masukkan nilai Y di sini sebagai delta. Kenapa? Kita tahu delta adalah distance of Y from U equal to 0 to U equal to 99%. Or in this question, we aim for U is equal to capital U. So This is the value of kinematic viscosity, and the x here is the length of the plate. So, and then you substitute everything, we could have this equation. And then we could calculate it. So the delta is 0.01839 meters. Okay, then, okay, let's say the question is, okay, please find the y location, means the location in y-axis, where u is equal 0.5 u. So what we need to understand by using this, by this term is, okay, so u is equal to 0.5 capital U, and then we could write u over capital U is equal 0.5. So means that we need to look at column of u over capital U. So this is the column of u over capital U. So normally we will take 5 because this is the 99%. But now we are aiming with 0.5, mean 50%. So according to this table, so we don't have 0.5, we have 0.48 and we have 0.6298. Okay, what we need to do is we need to do interpolation. So we need to get the value of 0.5 based on the ratio. So let's say we create new table here. Okay, based on the previous one. Okay, from here, so we, okay, from here we calculate like this one. So means that if u over u here is equal to 0.5, so we could use these two values to calculate other values. So we could calculate that eta is equal to 1.58, f eta is 0.39, f double prime eta is equal to 0.2993. So I hope you know how to calculate this one. So and then in this situation, please use at least 4 or 5 decimal because it will help you to get very precise answer. Because in boundary layer, if we calculate the thickness of boundary layer, okay, sometimes the unit is very small, okay, in millimeters maybe. So if you're not using the decimal, you just round up. Okay, so it's maybe will give you answer with big errors. Okay, so from here, so we calculate and we have a new table like this. So and then we could start calculate. So we need to calculate the value, the y location. So we use this equation. So and then from this equation, we know that eta is equal y u over nu x. So we need to calculate the value of y. So we rearrange this equation into this one. Okay, and then we substitute all the value. We know the value of eta, so we have the value of eta here. So and then we know the value of nu, which is the kinematic viscosity. We know the value of x, which is 2 meters, and the capital U. So in this situation, it is around 5 meters per second. So you substitute everything, so you will get y is 0.0038 meter. So what is the meaning of y here? So let's say we have a boundary layer here. This is the flat plate. So and then the boundary layer can be imagined like this one. So the y location is the location of y axis. So we have a 0.0038, maybe it's a stay here. So because we take x is equal to 2, so it's here. So this is x equal to 2. So this is the y-axis. So maybe the value is here 0.0038. Okay. Please ignore about this. Okay, so I hope you could imagine the meaning of x, the meaning of y, and the meaning of location that we calculated here. And then we go for the y maximum component velocity. So again, here it is actually the component velocity. So if our molecule travel from here to here, so you in ideal flow, you know that it has a u component here and v component here. Again, here it has u component and it has v component. And in this question, we need to calculate the value of maximum y component velocity. So this is the equation that we could get from textbook. It is okay for you to use this equation if this question being asked. Okay, however, this is not our syllabus, so it is okay. But at least you want to know this. So and then in previous question, so I use value here from table. Okay, now let's say if you want to calculate it, you still could calculate it based on the table here. So we know here that we have a 0.5. So and then we have f eta is 0.39. We have this is the f prime, and this is f double prime. So we have f double prime here. So according to this question, we will have 1/2 eta. So eta is 1.5862 times f prime. So according to here, so f prime is 0.5. So this is the value of eta. And then we need to deduct with minus f. So f here, if we see, it is equal to 0.5. I'm sorry. F prime is 0.5, and f here based on the table is equal to 0.39. So we substitute the value of 0.39 here, and then we could calculate the value of 0.0011586 meter per second. So means that previous table that I show you here, so it's actually the simplified version of this one. So if you want to use this table, please make sure that you calculate, because now we just now we need to use the value of 7.5. So you need to calculate what is the value between here. So it is 604. I'm not so sure the value for this one. So okay, so this is the way we calculate from the table. And then we go the question about what is the shear stress at U equals 0.5 U. So this is the equation. If you look back in to Blasius notes in our lecture, so we will discuss about this. Okay, on that note, okay, we use eta is equal to 0. Why we take eta is equal to 0? Because we need to calculate the shear stress on the surface. So normally we are calculating shear stress on the surface of flat plate, because this is the maximum shear stress occur in this situation. But if you calculate at U equal to 0.5, okay, means that here, okay, so means that you need to calculate at this condition. Okay, in previous notes, if you see, so at surface condition here, the value is eta is equal to 0. And then on that, in that notes, okay, I use eta equal to 0. However, so in this question, okay, we need to calculate the shear stress at this situation. So at this situation where U over capital U is equal to 5. So if we look into our table here, so if U over U is equal to 5, so the value of eta is 1.5462. So means that we need to use the F double prime eta at 1.5462. So we could get this value from, again, from the table, which is here. So you substitute the value of 0.2993. We have substitute the value of 0.2993, and then you could calculate all this value. So it is equal to 0.011 Pascal. So the value of X here is the length of the plate. Okay, so this is the notes about the velocity components. You could open your textbook, page 403. So it is come from the idea of Cauchy-Riemann equation, if you still remember. So if u is d psi over dy and v is minus d psi over dx. And v here it can be simplified as this one according to the Blasius, and for the u is according to this one. So I think in my notes I will only show you the value of this one, because we just assume that all the velocities move in x direction. Okay, but however in Blasius solution they use the differential form. So as you learn in chapter 1 and chapter 2, so now if we want to calculate very detailed, we could use the idea of this one. So means that the simplified version or the equation that you need to understand is this one. So this is the notes for the velocity components of the Blasius exact solution. Okay, so let's say we try to solve this problem, okay, by having a velocity profile. So let's say that, okay, just now we have a same flat plate, but we assume that the velocity profile is parabolic or second order polynomial. So from our previous lecture, so we know that the parabolic velocity profile can be written like this one. And then the parameter is u is 5 meters per second and x is equal to 2 meters. So if you want to calculate the shear stress, okay, so you need to start with the von Karman and then you need to get the value of shear stress. Okay, I'm not showing you the how to get the value of shear stress here, because you could refer this calculation in my previous lecture notes. Okay, if you do that, means that you use the velocity profile here. So you substitute with von Karman equation, you equalize with the Newton's law of viscosity, then you will get the value of delta. And then finally, you recalculate again the value of Newton's law of viscosity, you substitute the value of delta that you get, so and then you could get these terms. Okay, and then if you see the equation here, there are no differential form. There are no dx, dy, there are no d theta, dx, and so on. So means that this equation can give us the final value. So the final value of shear stress, if you substitute all the value of the parameter, it is around 0.01347 Pascal. So and then if you want to calculate the boundary layer thickness, okay, please refer our notes on how to get boundary layer thickness from second order polynomial. So we could get delta is equal 5.48x Reynolds number. So we substitute the value, we get 0.01344 meter. And then to calculate the maximum y component velocity. So here, because we are using, we differentiate using velocity profile. So we don't have any, because it is not possible for us to calculate by using that method. So means that if you still want to calculate the component velocity, we need to use the idea of ideal flow, and also we use the idea of differential form. Okay, means that we don't have any answer here. And then we go for the flow rate. Okay, the flow rate here, again, we are using this equation. So previously, this equation is equal to another equation which has f prime and eta. Because we don't have table, now we need to solve this equation by substituting the value of u here with the velocity profile that we have. But you must make sure, you must be careful, in this equation, okay, the parameter here is only small u. So mean what you need to do is you need to change. You need to change from this term, u over u, into this term, because this term will have u equal u capital U and so on. So you substitute all this equation into this one, okay, and then the width here is equal to 1, So, and then we could integrate with dy. So the simple one is you could bring with here and also the u here outside because it's nothing to do with y. And then you integrate this one, substitute with limit 0 to delta, and then you could get it is around 0.0448 meter cube per second. Okay, so means that now you could see clearly the way we solve the problem. It's come from the same idea, but for Blasio solution, normally it will change a little bit their form into the value that we could get from tables. But in von Karman, normally he will use equation to substitute into the equation and then to solve that problem mathematically. So, and then let's say we need to calculate what is the value of y location where u equal 0.5 capital U. So here, so the terms u equal 0.5 capital U can be written as u over u equals 0.5. Okay, so here we know that previously the velocity profile is given like this: u over u equal to y over delta minus y square over delta square. So, and then it now we could equalize it with 0.5 based on the question. So now, okay, let's say if we solve like this, 2y over delta minus y over delta square equal to 0.5. Means that you could solve this one. However, it might be a little bit difficult because we have one y with the power of 1 and we have another y here with the power of 2. So means that we need to solve this by using the idea of trial and error. Trial and error. Okay, you may use your calculator, your scientific calculator, to get the value of y. So the simple method to solve this one is by having, let's say we have here, we have y square over delta square minus 2y over delta plus 0.5 is equal to 0. Okay, if we bring here, so it become plus, so this will become minus, and 0.5 will remain is 0.5. So from this equation, okay, you may use Excel, Microsoft Excel. You could write a table here, and then you could give try and error method. So means, for example, you could predict the value of y. So let's say you give 0.01 and then you start to calculate until the total of this one is equal to 0. Okay, you may try this at home. So we could get it is around 0.00394 meters. Okay, the y location to get u equal 0.5 capital U.